Hi, today in this ICS Impulse video we will be talking about data analysis. Here you see the ICS Impulse device, a computer with the ICS goggles. Why do we do head impulse testing? Well, a head impulse test is an ear-specific test that detects disorders of the vestibular ocular reflex and identifies which ear is affected in cases of peripheral vestibular loss. How or where in the workflow do we provide this test? It's the first step towards diagnosis and subsequently early treatment. Since the head impulse test is quick and won't produce adverse patient reaction, it's recommended that the test be performed at the beginning of the assessment workflow. Let's talk about head impulse testing versus caloric testing. Well, first you'll notice that the head impulse test and the caloric test are both ear-specific tests. The head impulse test detects cases of peripheral vestibular loss in the lateral semicircular canal. And with LARP and RALP, it also looks at the anterior and posterior semicircular canal. The caloric only detects cases of peripheral vestibular loss in the lateral semicircular canal. So with a lateral head impulse and LARP and RALP, you can test all 6 of the canals, both the lateral canal and the anterior and posterior canal, whereas calorics only allow you to assess the lateral canal. The head impulse test tests at frequencies 4 to 5 hertz, which is stimuli replicating the patient's everyday situation. A caloric test tests at a low frequency, 0.025 hertz. So again, a head impulse test is testing how the patient truly uses their vestibular ocular reflex. The other advantage to head impulse testing is the stimulus doesn't persist between tests. So you can do a leftward head impulse, and then you can do a rightward head impulse, and then you can do a whole nother test session, and there's not persisting effects from the last test session. Whereas calorics, if done properly, you should wait 3 to 5 minutes between each temperature and between the ears. If you do not wait, then the temperature effect still remains, and therefore the stimulus can persist between irrigations. Now let's look at head impulse test results. The first test result we're going to talk about is looking at a patient who has normal results. So what we should see is the gain, and this is the comparison of the eye to the head movement. The gain should be greater than 0.6. There may be a few catch-up saccades, but nothing of significance, and this patient could have spontaneous nystagmus or not. Here's an example of a 2D graph from the ICS Impulse system. What you see over in the left-hand side is the gain graph. Then you have the head for a rightward head impulse, and then the eye movement. And if you look at A, if you compare the head to the eye, they look very similar, and that is why all the gains are above 0.6. They're actually, the average of this right gain is 0.87. If you look over here at B, you have these downward spikes. Those are actually from spontaneous nystagmus, and we'll talk more about spontaneous nystagmus a little later. So again, the gains are within the normal range, the white range here, and then you see the head movement and the eye movement. Here's a 3D image of that same patient. Gain graph still looks the same. And then you have the head in the salmon color and the eye in the green color, and you can see the spikes down below of the spontaneous nystagmus. So what do you have with a patient who is exhibiting overt catch-up saccades? Well, first thing on the gain is less than 0.6 and is within the abnormal range. It's 0.1 to 0.6 if it's a unilateral loss, and typically less than 0.1 if it's a bilateral loss. You will also see overt catch-up saccades, and these are catch-up saccades that actually happen after the head impulse stops. So after the head stops moving, then the eye moves back to the fixation dot. Typically, overt catch-up saccades can be picked up with the naked eye or using visual observation. And a patient with overt catch-up saccades may or may not have spontaneous nystagmus. Let's go to headimpulse.com and look at a patient with overt catch-up saccades. Again, you can access any of these videos on headimpulse.com. So we're going to look at this patient here who has overt catch-up saccades. Let's make this big. So there's a rightward head movement, and you see the catch-up saccade. There's the saccade. There it is again. There it is again. There's again. So it's pretty obvious that this person has catch-up saccades. And then they're going to show you in slow motion as well. So head turns, eye looks back to the fixation dot. One more time. Rightward. Head's turned, and eye looks back. But as you see, even with the regular recording, the regular speed, an overt catch-up saccade is very easy to see with the naked eye. Now let's look at impulse data for a patient with overt catch-up saccades. It's not the same patient that's in the video, just so you know. So if you look over in the gain graph, we see all the gain dots. The comparison of head to eye is within the abnormal range, the gray range. And this is unilateral. It's between 0.1 and 0.6. So the right side's normal, the left side is abnormal. Here you have the left head impulse, and then the green is the eye. So if you look at the comparison to head movement to eye movement, you can see the eye movement is reduced, is smaller than the head movement. And then you see these catch-up saccades. So what's happening is the eye is actually moving with the head and then jumping back to the fixation dot. Let's look at the 3D image. And here you see the eye is in green and the head is the blue movement. You can see the vestibular ocular reflex is definitely reduced in this patient. And then we have all these catch-up saccades over here to the right. Again, white is normal, light gray is unilateral loss, dark gray is bilateral loss. And this patient has a unilateral left weakness, and therefore their gains for the left side are abnormal. Now let's talk about someone who exhibits covert catch-up saccades. So again, their gain is going to be similar to an overt catch-up saccade. It's going to be less than 0.6, and it's going to be 0.1 to 0.6 if it's unilateral, and less than 0.1 if bilateral. But the difference is a covert catch-up saccade occurs during the head movement. So they're going to jump back to the fixation point while the head is still moving. And this cannot be identified with the naked eye. It'll be missed if you're using visual observation. And this patient may or may not have spontaneous nystagmus as well. So let's go back to headimpulse.com and look at somebody with covert catch-up saccades. Okay, so we're going to look at this patient here with covert catch-up saccades. Let's make it big. So really look, can you see the catch-up saccade? It's very hard to see with visual observation. Now they're going to slow down the video. Head moves. Now the rightward. Head moves, and there's the catch-up saccade. Okay, so again, you can see all those videos on headimpulse.com. Now let's look at the impulse data for a patient with covert catch-up saccades. So here's the 2D analysis. And here's your gain graph again. And this person is abnormal on the right side, normal on the left side. Not the same person you saw in the video, somebody else with covert catch-up saccades. So you have the right side here, and you can see they're all within the abnormal range, that gray range between 0.1 and 0.6. So this is a unilateral loss. You have the head impulse here in orange, and then over here in the green you have the eye movement. So if you look at the head movement to the eye movement, you can see that the eye is reduced, so the vestibular ocular reflex is not performing normally. And then you have all of the catch-up saccades. And notice that the catch-up saccades for covert are actually closer to where the eye movement is, because those are occurring during the head movement, whereas overt occurs after the head stops moving. So now let's look at the 3D analysis. So the salmon color is the head, the eye is the green. You can see the eye is definitely reduced in comparison to the head, and you have all of these catch-up saccades over here. Just to give you another picture, if you look here, here's normal, overt, and covert. And what I basically wanted to show you is that if you look at the overt and the covert, you can see that overt catch-up saccades are further to the right, and the covert catch-up saccades are further to the left, closer to the head movement. And that's very important. Again, overt occurs after the head stops, covert occurs during the head movement. Now let's talk about spontaneous nystagmus. Spontaneous nystagmus due to acute peripheral vestibular loss beats to the healthy ear. So if the person has a leftward abnormality, the spontaneous nystagmus is going to beat rightward. If you think about head impulse, when you turn the head leftward, the eye actually moves rightward to stay on the fixation dot. Okay? So let's look at this. Head impulses to the affected side have spontaneous nystagmus beats in the same direction as the catch-up saccade. That's again, if you've got a leftward abnormality, which is the example here that's circled in A, the head moves left, the catch-up saccade is right, but the spontaneous nystagmus is also beating right because the abnormality is on the left side. So you have not only the catch-up saccades here, but you've got the spontaneous nystagmus beating upward as well. Now let's talk about what happens if you're testing the non-affected ear. So head impulses to the healthy side has spontaneous nystagmus that beats down. Again, it's a left side abnormality. You move the head rightward, the eye is moving leftward to stay on the fixation dot, but all the spontaneous nystagmus is still beating rightward because it's a leftward abnormality or left-sided abnormality. So all of these spikes down below are the spontaneous nystagmus. And again, if you look at the gain graph, you can see the right side, which is the solid dots, is within the normal range, and the left side, which is the open circles, is in the abnormal range. Let's talk some more about data analysis in the ICS impulse device. Okay, let's go in the software. Click on Patient List, and what you'll see is you have 3 demo data: a normal example, a covert, and an overt example. And these are the ones we just talked about, but I want to show you where you can access the 2D and 3D graphs in your software. So if you open up one of these patients, let's go to Overt. Here's the 2D analysis. So the lateral impulse tab is where you do your collecting the data. Then you have your 2D analysis here. Head right, head left, eye right, eye left. Again, right side was normal, left side was abnormal. And then if we click on 3D analysis, you notice that you've got your 3D graphs. In all of these tabs, you can always make an image larger. So if I click there, I can make this image larger. Let's kind of use my mouse here and make this big. And if you hold down the left mouse key, you can turn the 3D analysis around and look at the 3D analysis comparing the head to the eye. Let's put that back where it was. Let's go back to our presentation. So that's where you access the 2D and the 3D analysis. So again, in the ICS analysis, you've got that 2D and 3D, and like I showed you, you can rotate it the 3D 360 degrees. You have the gain graph with normative data, which we've talked about. We're going to talk about the test info, and then we're going to talk about how to compare multiple test sessions. So here's the gain graph. As I said before, white is within normal limits, light gray is unilateral loss, and this dark gray band below 0.1 is bilateral loss. Down the bottom left, you also have the mean, or the average of all the right gains. And in this patient, it's 0.87. And then you've got the average of all the left gains, which is 0.41. And the standard deviation of each of those. If you want to just display a right one or a left one, then you can uncheck the box. So what you have here is the gain and the peak velocity. And that's the peak velocity of the head impulse. So, again, right is red and left is blue. And the peak velocity is the maximum velocity representing that particular head impulse. And then here is the publication where the normative data was taken from. Under the options window, under lateral head impulse, those cutoffs for the normative data can be modified. Under test info, what I want to talk about here is the difference between accepted and collected. There's actually 2 algorithms that assure that you collect accurate data and that you analyze accurate data. So the first thing is the collection algorithm. This actually occurs online while you're doing your head impulses. So over here in the black, 20 and 20, that's what the default was set to, that you need to collect 20 head impulses to the right, 20 to the left, before it automatically saved the data and analyzed it. This actually tells you how many were actually collected or passed through the collection algorithm. So 20 to the left and 21 to the right, and 6 were rejected. So that means that when you're doing the head impulses, all that raw data goes through a collection algorithm, and it decides whether or not that is a good head impulse or not. Then all that raw data again gets reanalyzed through a second algorithm. So it's not just the collected data that gets reanalyzed, it's all the data that gets reanalyzed in that second algorithm. In that second algorithm, which is our analysis algorithm, it tells us that 22 were accepted for the left, 21 were accepted for the right, and there was 4 rejects. Now these numbers don't always add up. Like you won't always have 27 on one side, on the collected side, and 27 on the accepted side. If your head impulses are performed properly, these two numbers are real close. But if you're new at doing head impulses, you might see that these two numbers are not as close, and that a lot of your collected data wasn't accepted because it really just wasn't that good. The accepted algorithm is actually more detailed and looks at more characteristics of the head impulse data to decide whether that's a good head impulse or not, and whether or not that data should be analyzed. So what is collected is what you see on your collection screen until you get your 20 on the left, 20 on the right. What's in the accepted is actually what is presented in the 2D and 3D graphs. On this test info tab, you also have the test date and time, who the operator was, what the average frame rate was for that test, what the calibration values were, and if you checked that the patient had spontaneous nystagmus, then this box would be checked. So again, we've talked about this. The accepted number, so there's two different algorithms. Remember this, there's an accepted analysis algorithm and there's a collection algorithm. And just so you know, if the frame rate drops below 219, there will be a yellow message that comes up on your screen that says the frame rate is running too slow to collect data. This shouldn't be a problem if the computer you're using meets the specifications and that you don't have a lot of programs running in the background. But if you run into an issue where the frame rate is too slow, then go to the troubleshooting section of the user manual and follow those steps. Now, you can compare multiple test sessions. So this is an example in progress graph where there's 2 test sessions, and you can look at up to 5 test sessions, I believe, for the 3D. All of these 3D images you can rotate just like you can in a single 3D image. And then if you want to look at the gain graph, you can go under progress data. So this shows you the first test session in dark blue and red. The patient, the right side, was abnormal. And then the second test session, the patient was within normal limits if you look at the pink and the turquoise. So then you can look at data. So if someone has vestibular neuritis and they recover from it, you can compare an abnormal result to a normal result or see if therapy is helping as well. So you can look at the progress of the patient between test sessions. That's all I have on analysis today. So stay updated and learn more. You can go on ICSimpulse.com and look at lots of other videos. And headimpulse.com gives you the research behind the Impulse device.